Earthquake forecasting remains a significant challenge due to the complex nature of the factors involved and the limitations of current technology and understanding. Here are the primary reasons why earthquakes cannot be forecasted with precision. Number 1 is the complexity of Earth's crust. The Earth's crust is composed of different types of rocks and materials with varying properties, which makes predicting how stress will accumulate and release difficult. Earthquakes occur due to the movement of tectonic plates, but these interactions are extremely complex and not fully understood. The stress and strain that build up in the Earth's crust do not have uniform or predictable patterns. Number 2 is lack of observable precursors. Unlike weather forecasting, where certain observable conditions can reliably predict outcomes, earthquakes do not have consistent detectable precursors. Some potential signs, like foreshocks, gas emissions, or changes in groundwater levels, are not reliable indicators because they do not occur before every earthquake and are not unique to earthquakes. The signals that might indicate an impending earthquake, such as minor shifts in the Earth's crust, are often too subtle to detect with current technology, especially considering the depth at which many earthquakes originate. Number 3 is scale and time frame. The buildup of tectonic stress happens over long periods, decades to centuries. Predicting exactly when this stress will be released as an earthquake is beyond our current capabilities. Earthquakes can occur along fault lines that stretch for hundreds of kilometers. Identifying the exact location and timing within such a vast area adds another layer of difficulty. Number 4 is limited historical data. Human record-keeping spans only a few thousand years, whereas geological processes operate over millions of years. This limited data makes it challenging to identify patterns or cycles in earthquake activity. Historical and geological records of past earthquakes are incomplete, especially for regions that are not well studied or have not experienced significant seismic activity in recent history. Number 5 is technological limitations. While seismic monitoring networks have improved, they are not evenly distributed around the world. Many regions lack the dense network of sensors needed to capture detailed data about seismic activity. The massive amount of data generated by seismic sensors requires sophisticated algorithms and models to analyze. While advancements are being made, our current models are not yet capable of accurately predicting earthquakes. Number 6 is current research and advances. Although long-term forecasting is not yet possible, early warning systems can provide alerts seconds to minutes before the shaking from an earthquake reaches a location. These systems rely on the detection of initial, less destructive seismic waves, P waves, that travel faster than the more damaging waves, S waves and surface waves. Scientists are continuously researching to understand the mechanisms of earthquake generation better. Advances in machine learning, AI, and better monitoring technologies offer hope for improved prediction capabilities in the future. In summary, the unpredictability of earthquakes stems from the complexity of the Earth's geological processes, the lack of reliable precursors, the immense spatial and temporal scales involved, limited historical data, and current technological constraints. While significant strides are being made in understanding and monitoring seismic activity, accurate short-term forecasting remains an elusive goal. However, early warning systems and ongoing research provide hope for mitigating the impacts of earthquakes and improving preparedness in the future.